My name is Ernest Worthman. Hello, everyone. Welcome to the 6G Symposium. This is the Spectrum panel. My name is Ernest Worthman, and I will be moderating this panel. We have a great panel lined up with some of the most esteemed industry and academic speakers presenting. 6G will be working in both submillimeter and millimeter wave spectrum. Challenges below 6 gigahertz are the most pressing since this is a spectrum already full of wireless players. Thus, there are major issues with spectrum utilization and spectrum sharing. In this spectrum, 6G will be eyed as the platform to address both of these. In the millimeter wave spectrum, there are different challenges. Many have to do with spectrum propagation, since we all know how difficult it is to propagate millimeter wave signals higher up, especially point-to-point and point-to-multipoint, or I should say rather than other than fixed point-to-point or multi-point. The mobile type of propagation is what's going to be the hardest to become. And it becomes, orders of magnitude more challenging to look at spectrum beyond 300 gigahertz. This session will provide some insight, hopefully, into these challenges, and let me introduce our speakers. First speaker is Alexander Damjanovic, who is the Radio Working Group Chair, MFA, and Principal Engineer and Manager at Qualcomm. We have Joseph Jornet, a professor at Northwestern University, Andrew Clegg, Spectrum Lead at Google, and Manisha Ghosh, Professor, University of Chicago. Welcome, everybody, to our little party. I'm going to jump right in because we have an hour and I would like to get most of this into the discussion. So one of the first questions I'm going to ask, is what are the benefits of non-licensing or non-exclusive licensing, and what are the suitable deployment scenarios? Alexander, would you like to start out?
Yes, thank you, Ernest. So non-exclusive licensing is an important aspect when we talk about cost reduction of new, for example, 6G deployments. A significant part of the cost for an operator would be acquiring the spectrum. So when we talk about non-exclusive licensing, we have the non-exclusive licensing between the new licensee and the incumbents, but we also have the non-exclusive licensing scenario when there are even no incumbents, and then we have shared licenses for specific band. So shared licensing can basically reduce cost, and that would bring down the service for 6G. And in addition, with shared licensing, we can leverage some of the work in Open RAN on shared equipment and further reduce the cost of 6G deployments.
Sorry about that. Monisha, this one's for you. Is the spectrum that we have currently allocated for both unlicensed and licensed services being used efficiently, or is there room for improvement?
Thanks, Ernest. So as we all know, most spectrum today that are used for commercial services like Wi-Fi and cellular, it's either licensed and huge amounts of money are paid for it, or they're unlicensed. I think by and large, as consumers, we have benefited from these two spectrum modalities. However, of late, we have seen a lot more usage of unlicensed spectrum by cellular operators, which in my mind is a very good thing because it really allows spectrum to be utilized in the best possible way. However, I don't believe enough thought has been put into making sure that coexistence works out better. I think as we look forward to the future, sharing either in the purely unlicensed manner or license sharing or other modalities are going to become more common in the mid-band. It's not a secret anymore that there is very little spectrum left there, and the definition of mid-band is changing too. So we are already, it's not sub-6 anymore. We already have the unlicensed 6 gigahertz band, and there are bands all the way up to 12 gigahertz that may be used for sharing. So we are in a, I think there are a lot of technologies that have been developed to make sharing work better. I think we're not there yet. And part of it is I would encourage standards bodies to work closer together to make sure that when you're designing a system, you design it natively with sharing in mind and not something that you add on after you've built your 3GPP system end to end and then figure out how do we coexist in shared spectrum. So it definitely can be improved.
Alex, this one's for you. Based on your experience with, well, let's see, am I muted? Make sure I'm not muted here.
No, we can hear.
You can? Okay. Based on your experience with CBRS and, of course, 6 gigahertz AFC, and assuming spectrum sharing will be given for meeting some needs of 6G and beyond, what are the improvements that need to be made in spectrum sharing technology to open up more spectrum for shared use?
Yeah, Ernest, I think that one was for me.
Yes.
Yeah, so so we've had a lot of experience. We've deployed a spectrum access system in the U.S. Citizens Broadband Radio Service Band now for 18 months. We're also designing a 6 gigahertz automated frequency coordination system. One of the things we've learned about the challenges of spectrum sharing is that it takes a lot of time to implement. So for example, in the CBRS case, from the time that the FCC issued its order that basically set out the rules for CBRS to the time where commercial service in CBRS was actually authorized, that span was 4 years of time. And then issuing PAL licenses was another 8 months beyond that. So well over 4 years. So it took a long time to go from the scheme to share spectrum to actually implementing it. And that time was consumed, about a little more than half of that time was the standards bodies putting the standards in place to figure out how this sharing was going to work. And then the other half of the time was the government certifying the spectrum access systems to make sure they work appropriately. So I'd say from my perspective so far, one of the biggest challenges to implementing spectrum sharing is the time frame it's taking to get the devices standardized and certified. And we need to find a way to make that process a lot more efficient. What we need to do is we need to look at what we've done in TV whitespace and CBRS and in AFC, and we need to find a template for spectrum sharing, and we need to apply that template to future bands where we don't have to go through the whole standards process and the certification process that we went through for CBRS. So to me, there's many things, there's many lessons learned, but the time scale to achieve spectrum sharing after we decide to do it is one of the biggest challenges I've seen.
Thank you, sir. I'm going to stick with that 3.5 megahertz or that mid-band, 3 gigahertz mid-band area for a little while and ask some questions, sort of a round robin or open forum. Spectrum sharing has been a topic that's been thrown around everywhere with everybody from government to private industries to incumbent users to those whining to get some new spectrum. Some of you are aware with the issues with Legato perhaps and some of these other people. And Joseph, I'm going to get to you about terahertz shortly, but I want to stay here for just a minute. And you're welcome to, I'm going to have everybody chime in on this. So how when we get all this done, especially in the 6G space, how is spectrum sharing, and you touched on this for a minute, Andrew, how is spectrum sharing going to become more or less a de facto platform for all of the players that want to get in there in the mid-band and up to 12 gigahertz even? Monisha, let's start with you.
Sure, and that's absolutely true. I don't think any band has come up in the recent years where some aspect of either sharing with incumbents or moving incumbents out has not come into play. So if we took a look at what the FCC, and I had the good fortune of being at the FCC at the time when the 6 gigahertz rules were made, right? Andrew Clegg talked about the AFC piece of the 6 gigahertz rules. And we fully realized that, yes, it takes time to set up an AFC. And if we were to not allow that band to be accessed until the AFC got set up, it would be too long. However, if we came up with another way of sharing and the knob that we turned there was on power, that if we could figure out a way to keep devices indoors and give them a lower power to transmit in, then maybe you could share without using an AFC. And that did get a lot of pushback there. I mean, and still the FCC, I think, is facing a lot of pushback on the decision it made to do that. But we went ahead and made the rules on that basis. So that was a little bit of a departure on, the database method of sharing. But that allowed, I mean, today you can go out. The rules have been out for just about a year. The first 6 gigahertz access points went on the market in 6 months. I have an 6 gigahertz access point and phones and devices that I'm experimenting with already. So as we look forward, we have to think of different ways of sharing. I think as a community, we are very stuck on spectrum sensing and databases as the only ways of moving forward. We have to be more innovative. We have to try new modalities. This indoor-outdoor sharing was one. Maybe there are others that are worth sharing. So an open mind, and also I think everybody, incumbents, newcomers alike, have to get used to the idea that you cannot be protected from interference all the time if you're sharing. Sharing comes with some tolerance to interference and some ways of managing it. That's either through power control, through your protocols, through better filter design. You mentioned Legato. A lot of that Legato debacle could have been avoided if people build better receivers. So the topic of receiver standards has come up very often within the FCC as, again, a mean to enable better spectrum sharing. So we have to learn from what we've done and then be more innovative in the future. You're muted.
Sorry. So it all comes down to what we want to do and what we can do in the end. Joseph, how about you chiming in on this one? And if you want to move up to the higher frequencies with similar concerns, feel free.
That's what I was going to say, which is that many of the problems or the challenges that have been faced in the mid bands or in the lower bands, believe it or not, are going also to show above 100 gigahertz. And last year it was in the 6GSymposium that we had a panel on conquering the spectrum. And we use the word conquer as if no one else was there, but even above 100 gigahertz, we have to coexist with users that have claimed several frequencies for over 20 years at this point. And well, those users happen to be again on satellites, and yes, we can interfere with them. So all the knowledge, what's being learned in the lower frequencies will eventually have to be adapted, improved, modified to make it compatible with above 100 gigahertz. And for those who don't know who I mean by coexisting above 100 gigahertz, well, we're mostly talking about passive Earth exploration services based mostly on satellites. And yeah, as probably was mentioned earlier today, right? One of the goals for 6G is to get to terabit per second. For that, you need huge bandwidth. Even if sharing at lower frequencies, it's difficult to find those bandwidth. So you need to go to higher frequencies. And surprise, you go above 100 gigahertz and you see that maybe you don't have those beautiful contiguous bands that you thought you had. So you will have to share them too, one step at a time. First, let's share the lower ones. Let's get the systems to work at those frequencies. Then let's talk sharing.
Alex, your take?
I completely agreed with Monisha that we need new ways of sharing to have more efficient protocols. Also, regulations should encourage sharing. And just to add one more aspect is that, as we all agree, there is not much available bandwidth. So if we're gonna find some bandwidth in mid-band and then try to divide among operators, each operator would not get significant bandwidth. It would be much less than if we try to efficiently use what we find available. So it's inevitable if we are talking about high data rates and new systems that improve upon the existing 5G system, that we would need larger bandwidth. And then the question is how we find that much bandwidth, not just for one, but for multiple operators. So spectrum sharing to me seems like the most obvious way to use in next generation systems, and those systems need to support it from the beginning natively, not that it's an add-on or afterthought like it was, for example, for 4G.
Thank you very much. Andrew, I'm going to start out with you on this one. And again, we're going to round robin in and get answers from our other panelists because I think it's practical for everybody. And, realistically, what role do you expect millimeter wave and terahertz frequencies to actually play in 6G once we get a firm grasp on what we're looking at?
Yeah, I mean, obviously Joseph will have the most informed, Joseph and Monisha most likely will have the most informed responses on this one. But, the Defense Innovation Board, I think it was last year, maybe the year before, released a study where they looked at the use of millimeter wave frequencies and beyond for broadband delivery, not just mobile, but regular fixed broadband as well. And the conclusion is the propagation situation is, as everyone knows, is very challenging. It's very hard to do any kind of broad mobility coverage at millimeter wave and certainly beyond millimeter wave. I like people who study millimeter wave propagation. I joke with them, it must be like the easiest field in the world because basically, out to 100 feet or so, it's great unless something's in the way, and then it's horrible, and that's all you need to know. The point is the cost of deploying substantial millimeter wave infrastructure that can cover significant mobility is just cost prohibitive. That's what the Defense Innovation Board study sort of concluded. It would cost, just an enormous amount of money to develop any significant penetration coverage in a mobile broadband environment. I think in certain cases you're trying to cover a room or a very limited area outside with point to multi-point or something. And I think it's doable. We even have a service that uses 70, 80, and 90 gigahertz to do broadband transmission among buildings and cities and things like that. So I think there are limited targeted opportunities for millimeter wave. But I think as far as a mobility environment, and others may disagree with me, but I think that's beyond 6G. I don't think 6G, if you think of 6G as being the 2030 kind of time scale, I don't think we're going to meet mobility at millimeter or sub-millimeter frequencies by time for 6G.
Interesting perspective. Thank you for that. Monisha, your thoughts?
Yeah, so as part of my research, we've been doing a lot of measurements on deployed millimeter wave systems in Chicago. And on the one hand, I'm truly impressed by how far the technology has come. So there are areas in Chicago where networks have deployed very densely. They are aggregating 800 megahertz channels. So you're getting 800 megahertz of download onto your phone, up to 2 gigabits per second, dense deployments. Pedestrian mobility is pretty good when you have such dense deployments. But on the other hand, looking at the results we have, I'm still a little bit unsure as to what the true applications are that this is serving. It's on the streets of a city. That signal does not penetrate indoors. We have a location on our campus where there's a millimeter wave base station right outside a dorm. And we went inside the dorm and we tried to make measurements. And if the window was cracked open just a bit and you had line of sight to the panel and the signal came right in and you put your phone right there, yes, you got your 1 gigabits per second. But other than that, you got nothing. So the use cases of this technology have to be thought out more carefully. Having said that, as a researcher and somebody who's funded a lot of research programs in terahertz and millimeter wave, I do feel the research on this has to continue. It is a frontier. We have to fully understand what the capabilities are. And we've got to find where it truly fits. So for example, within O'Hare, inside the airport, Verizon has deployed millimeter wave cellular in there, 5G millimeter wave cellular. And it makes perfect sense to have it in an indoor environment where you're not fighting, going through walls, and you can do a dense deployment. There are a lot of people, so you're serving a large customer base. But the whole concept of having a mobile cellular network that is on millimeter wave or terahertz, I think we have to be very careful. Just because the technology can make you get there, I'm not sure we should, because there are a lot of other things that we need to consider.
Yeah, it's a very interesting perspective. We all know, the propagation characteristics of millimeter wave, and it's flaky. I mean, the higher you go, the harder it gets. But Joseph, you want to chime in on that one too?
Absolutely. So what I would say is, as much as I love terahertz communications, and that's what I did when I was from the day I was a PhD student, so it has been several years now, or many years now, is that, first of all, what is terahertz good for, right? And at the end of the day, what the terahertz band, or let's say any frequency above 100 gigahertz, what it's good for is that you get very large bandwidth. If you don't need the bandwidth, you have so many more problems to address than benefits that probably you don't need to go to these frequencies. And many times I get people reaching out saying, oh, Joseph, wouldn't it be cool to put this terahertz on this thing? And I said, why? I mean, it could be cool, yes, but what do I get out of it? And many times it's not clear. So too many challenges for not that many gains. So which is the gain? It's data rate. Which is another way to sell high gains, meaning high data rates? Well, it also allows you to talk very fast, which also means that it's difficult to intercept what you're saying, which means that it's intrinsically a secure system. Everything that we're saying, from something that is challenging to propagate, it also means that it's challenging to intercept. So there is that edge component. And one of the things that I would like to add is that, well, maybe we cannot yet envision how we're going to use these higher frequencies in the front haul, but clearly in the concept of wireless backhaul, it makes sense. Whether that wireless backhaul is in areas where we could have an optical fiber, which doesn't make any sense, or in areas in which you cannot deploy optical fibers, or maybe because of technological reasons, financial reasons, geographical reasons, but also, backhauls that may not be on the ground, may be up there, because as you know, as we go up in the atmosphere, we don't find obstacles and we find less absorption, which is the problem for terahertz signals. So there are several efforts right now going on non-terrestrial networks based on terahertz signals, not for the up and down links, but for the cross links. So I would not ignore that side. One last thing that I wanted to add is that this very large bandwidth comes with very small wavelengths too. It's also good for sensing. So there have been some discussions on how you can take advantage of these terahertz, not just for communications and radar, which is what comms and sensing usually means, but also communications and sensing, where sensing may mean, for example, air quality monitoring. So there are things that are not the traditional ones, and I don't know if they will be in 6G or 7G, but certainly, as Monisha also said, the research needs to continue to unleash the full potential of this spectrum.
Thank you, Joseph. Alex, what do you have to say?
I also want to basically tie into the question in the chat, is that how we can improve millimeter wave coverage. We certainly have challenges with millimeter wave, but we need, basically it's just an opportunity for new solutions. So smart repeaters are definitely one way how to address coverage. And the other potential solution that we could look at is the concept of UE cooperative communications that is now being studied in some forums like NextG Alliance, or proposed to be studied, where we don't look at the communication link as one link between the base station and the targeted user, but rather in dense deployment, see a group of users as a target and allow them to basically forward data to each other if they represent a cooperative group. So definitely there are challenges, but those are just opportunities for new research and solutions in 6G.
Perfect. Thank you so much. Go ahead.
Yeah, if I may just add something to that. I think there is a lot of, I've heard talk in the media and others about how it was a mistake for the US to focus so much energy on millimeter wave for 5G. And I actually disagree on that aspect, because I truly think that by being early leaders in this space using millimeter wave, we are way ahead of the rest of the world in really understanding the limitations of this technology. And so we can work towards solutions faster than the rest of the world can. So it has put us in a leadership position, which we shouldn't back away from at this point and then just retreat into the mid-band again. So I think we have, as a country, enough resources to pursue both mid-band and high-band research.
Anyone else want to redirect? If not, let's take a look at, so as new technologies evolve and new spectrum becomes available, what are we going to do with older technologies in these spectrums, or in the spectrum, well, spectrums, different bands, and how do we keep efficiency growing all the way from, let's say, 900 megahertz up to 200, 300, 400 gigahertz? Joseph, let me start with you.
Absolutely. So one of the comments that I many times get is like, oh, so how is terahertz going to solve this problem or that problem? And I'm like, no, maybe we don't need to solve this problem at these higher frequencies. We're going to keep using the lower frequencies too. And in fact, I think that that's what they do. We need to complement the different frequency bands for what they are good at, right? With terahertz networks, I just throw a crazy thought. We're used to deal with networks in which everyone is connected. And when we're not connected, we panic and we try to fix it. Maybe that's how the lower frequency networks should operate, and that's good. But maybe at terahertz frequencies, we need to operate in a different way, which is like, generally, we are not connected. And when we're connected, we just make the most out of that, at this moment, very beautiful channel. Maybe it will last just a couple of seconds, but when it lasts, it's great. So to me, it's not about the new technology replaces the old. All these technologies need to coexist. All these technologies need to be kept advanced. And there are many advances that populate across and are true. For example, in the last few years, the concept of intelligent reflecting surfaces has become very popular, especially at lower frequencies, mostly to enhance capacity in some scenarios. Fine. Well, at terahertz frequencies, we have been working on intelligent reflecting surfaces for years because that was our only way to get away the lack of line of sight. But it's one fundamental concept, engineering reflections, that applies to the different frequencies and improve the performance of the different frequency systems. So I think that that's one of the ways that we should move forward, which is we don't abandon technologies, we think how to better complement them, and that will pay probably some cost, on how to integrate them and make them work together, but I think that's how we should move.
Andrew, your turn.
Yeah. I was looking at one of the questions that was typed into the chat from Doug Castor, and I sort of agree with him, and it's what I alluded to earlier as well, and that is, I think it's going to be a long time before. So even in my opinion, even moving to millimeter wave for 6G, where millimeter wave means 30 gigahertz and above, may be a little premature. Certainly moving to terahertz for 6G is premature, in my opinion. And I know NextG Alliance and others are looking at terahertz for 6G, but I don't think we're going to get to the technology and to the use cases where it makes sense. Joseph's comment about, sort of opportunistic use of millimeter wave channels or terahertz channels or whatever, that's quite interesting. I have to, think about whether that meets the typical user profile. So I agree with Doug that I think, certainly terahertz is 7G and beyond, and is not something that's going to be prevalent at 6G. With regard to the original question, first of all, I'll say something I don't think any of us have said yet, and that is, I think there's still a role for exclusive use spectrum. I think there are networks and there are use cases and there are quality of service guarantees and things like that really benefit from exclusive use, the way that the large mobile carriers are using spectrum right now. I think there's always going to be a role for exclusive use. But as everybody has noted, it's getting harder and harder to find bands to clear. But then, you ask the question, well, exclusive use licensees currently have spectrum at 600 megahertz, at 700 megahertz, 800 megahertz, 1.9, 2.1, 2.3, 2.5. It goes on and on and on. and yet we're talking about clearing more spectrum, 3 gigahertz spectrum and other spectrum to make even more room for 6G and beyond. And in my opinion, we've got to look at recycling some of these previous bands that they've used. It may not have the contiguous bandwidth necessarily that they need, but if that's true and they can no longer be used for 6G because it doesn't have the right technical characteristics, maybe it should be refarmed for something else. Who knows? But I think we need to look carefully, instead of declaring that certain bands just need to be cleared and reallocated to flexible use or whatever. We need to look carefully at the hundreds of megahertz that actually 1,000 megahertz that have already been allocated to what amounts to commercial broadband mobile systems. So I think we need to use them more efficiently, and we also need, when we look for 6G spectrum and beyond, we need to look at reusing spectrum that we've already been using for first G, second G, third G, 4G systems as they've evolved. So, I think we need to take a close look at spectrum that's already allocated for exclusive use.
Interesting. Let me come back to these questions near the end of the session. We'll address them in the Q&A back at the back end of this, because I want to keep on topic with what we were talking about. And I'm going to narrow that question down that I had asked before. What are we looking at efficiently managing spectrum below 6 gigahertz going forward and sharing 5G and 6G? Let's focus on that for a minute. And Manisha, I'm going to give you first crack at that one.
Sure. And I'm going to tie it a little bit with the previous discussion. I guess if you look at how the cellular standards evolve, each standard, each G that comes up is not backward compatible. So it ends up needing new spectrum. As opposed to Wi-Fi, which has evolved many generations using the same spectrum because they designed their systems to be backward compatible. Of course, there's a price you pay for backward compatibility in the sense that you're losing a bit of efficiency. But I think the problem we are facing now as we look at 6G, just the other day, somebody asked me, does the FCC have 6G spectrum? I said, no, we don't have spectrum that's labeled for 6G or labeled for 5G or labeled for 4G, but that's somehow what it has become. So right now, for example, as we are looking to even find spectrum for 5G now, and we're thinking about 6G, we have to look back and look at spectrum that's still being used by 3G and even 2G in some places. So how do we process it so that as new generations of cellular standards come online, that we have a way to release spectrum that's used for previous Gs? But that brings up its own problem. There was a professor in the civil engineering department who was really upset that AT&T is shutting down their 3G network because she has installed sensors that work on 3G in a number of buildings in New York City. And now all those sensors are going to be worthless, right? So we have to be thinking much more carefully, maybe even 30 years down the line, that if we are deploying sensors with a certain G and they become, useless after 10 years, is that an efficient use of spectrum? On the other hand, do we just tie up 3G spectrum because, there are sensors out there that still use 3G? So I don't think we've thought through these issues very carefully. So if there are certain applications, so maybe it's the time to think about spectrum for certain applications. If you're talking about sensor networks or IoT, which are going to have a long lifespan, and they don't need a lot of innovation in terms of bits per spectrum per hertz, bits per second per hertz. Maybe we allocate a spectrum and say, you innovate there and you make sure that you're backward compatible to whatever you do in that spectrum, much like Wi-Fi does. So it's just a mindset of thinking about spectrum has to change as we go forward. Otherwise, we are never going to find spectrum for 6G. We're never going to find spectrum for 7G if all of these Gs keep staying around forever. There's limited amount of spectrum in the midband.
That's an interesting response. Alex, what do you have to say about that, refarming that spectrum efficiently?
When possible, we think we should be refarming spectrum. The problem is that, as Manisha pointed out, there are some legacy deployments that would be turned off, and that creates an issue. In my opinion, we should, with the new G, we should have a protocol that enable efficient so-called dynamic spectrum sharing, when the licensee can actually share the spectrum dynamically. I think 4G already provides some form of spectrum sharing capability due to the non-continuous waveform. 5G is even more suitable, and definitely 6G should be designed as a technology that natively supports dynamic spectrum sharing. We still think that we may end up in a situation that even after all that, we don't have enough mid-band spectrum for 6G, because 6G will have most likely wider bandwidth than requirements than 5G. And given how crowded the spectrum is already, and the fact that we have typically assigned multiple operators that dedicated licensed spectrum, we may have an issue in differentiating 6G as a service. So we should look at all that when designing 6G.
Joseph, 2 cents worth?
Yeah, I mean, I agree with what has been said. I think that, being able to enable retroactive compatibility would be great. We cannot fix the past, but we can address the future. And this is true for all the things we're saying. So this will have to apply everywhere. Yeah.
I'm going to put the egghead on a little bit and ask this question of all of you. Where do you see the technology going to improve spectrum sharing from the hardware and software perspective? And Andrew, I'm going to go with you first on that one.
Yeah, I mean, it really goes back to, I think, what Monish has said from near the beginning, that, spectrum sharing and adaptability and reconfigurability needs to be built into the hardware and the standards from the very beginning. One of our experiences in CBRS is that LTE systems aren't designed to be hopping frequencies. Yet in CBRS, because of the dynamic nature of the incumbent operations, the DoD radar, there are instances where we need an LTE base station in CBRS to vacate its channel and move to another channel, and they're not really designed to do that. That's not really the strength of LTE. So you really need systems that, when told to move frequencies or do some other adaptation, can do it quickly and seamlessly without impacting the user experience. And I think that needs to be built in to the hardware from the very beginning. And then, of course, keep in mind that if we're sharing spectrum in future generations, which we almost certainly will be, an important component of the software is not just the software that runs the base stations and the user terminals and things like that, but is the software that drives any spectrum sharing system that's built in that helps run all of this. And I think there are a lot of developments that can improve our ability to design software that can most efficiently share spectrum. One of the things, and I say this almost every time I give a talk, one of the areas that I think deserves a lot of attention is propagation models, because that's built into all of these spectrum sharing systems. And the current state of our propagation models is absolutely horrendous. We're relying on models that are 60 plus years old in order to enable sharing in the CBRS band in the year 2021. A lot of these models weren't designed for sharing scenarios. They were designed back to coverage, determine whether your broadcast station could cover an area or whether your paging station could cover an area. They weren't designed to predict interference from a shared spectrum environment over a distance of 400 kilometers or so, which is exactly what they're being used for today. So I think from the technology development area, and there's many different technology development areas I think are important to a future shared spectrum, but I think one of the most important technology development areas is propagation models. And at Google, we're working on developing a lot more advanced propagation models that take into account our geodata, our knowledge of building polygons and
Andrew, I'm gonna interrupt a little bit. I want to move on.
Sure.
Sorry about that, but thank you.
Sure.
Listen, I have got a slew of questions coming in, so we don't have but about 15, 18 minutes left. I'd like to start addressing them. Is everybody okay with that?
Yep.
Okay, so one of the questions is, can technologies such as those from Movandi bring millimeter wave services indoors? I think the obvious answer to that is yes, but if anybody would like to drill down on that, welcome to talk. And I think, Monisha, I'll start with you.
I'm sure there are technologies that can bring millimeter wave indoors, but my question is, why install something outside and bring it indoors? Why not install it indoors in the first place? What exactly is gained by doing that? And that is where I want to, circle back to looking back as to how data is being used, where data is being used. If data is being used mostly indoors, then install the millimeter wave station indoors, or install a high data rate Wi-Fi indoors, and have a broadband connection in. And otherwise, we are kind of, building something because we can build it, and then trying to figure out how to use it once we've set that on a pole outside.
Joseph, your comments?
Yeah, so I agree with Monisha here, which is like, yes, we can try to add additional devices to improve signals indoor. Like, I mentioned before, besides these repeaters of Movandi, there are people working on intelligent reflecting surfaces. They are perfect. They work for many things. But at some points you get, well, do I need this, or should I just put directly a new access point and a new indoor station to help? So I agree with that. Certainly they help. Is it the best solution? Well, maybe it's the current solution.
Alex?
I think this solution, I think it's more about the ability to deploy. Definitely, it's better to have an indoor access point close to a user if the user is indoor. But if you're talking about public networks, then we have to find a good model how operators can use indoor equipment where they do not own that site. So there is a room for improvement, definitely. Research how we can leverage hardware, basically how operator can access devices or equipment indoor, and then use them for public networks.
Excellent. This question is pretty much available for everybody, and it says, are there any new promising business models for the shared spectrum access? The interest to unlicensed band from the current market players are doing lots of research, but very little implementation of new models for use of shared spectrum. What's your take on that one? Andrew, I'm going to let you start that one out.
Yeah, I think there are. I think, private networks is an important one. And I think also an important, sort of sub-use case is the use of those private networks in contained facilities, like in assembly lines inside of buildings and things like that, that can help improve spectrum reuse. So factories, things like that. I think that's an important use case for shared spectrum.
Monisha?
So I'm an academic who worked a lot in unlicensed band sharing, and I was actually very, very surprised when a year or so ago we actually started measuring the deployments and we're taken aback by how much network providers have actually deployed, at least in the major cities. So on our campus in the university, we have many, many LAA access points. Downtown Chicago has got, every pole that has a millimeter wave base station on it also has a LAA access point on it. So I don't think this is something that needs to be incentivized. We have seen data rates of 300-400 megabits per second that operators can provide because they're aggregating 320 megahertz unlicensed channels, which is a big deal at mid-band to get 60 megahertz of spectrum that you didn't pay for. I think you will see this happen more and more. Of course, there is a thing, you need newer devices to be able to, your phone has to be able to receive LAA, but it is happening. I don't think the operators need any incentive to use unlicensed spectrum. It's free spectrum for them to take, and they're using it, and they will use it.
Okay, Alex, what do you think about business models coming up in shared spectrum that aren't around right now?
I think they will come up. We have these new private networks. We have also now support for standalone unlicensed spectrum 5G networks that just was standardized in release 16. Those products are being built. So my opinion, in a few years, we'll see more and more of them being deployed.
Joseph, what do you think?
So I would say that all the things that we mentioned before about the problems with the higher frequencies actually might help when it comes to spectrum sharing. So the fact that your signals do not propagate as far as you would like to, the fact that you're using directional systems, those all make, in fact, facilitate the use of the same spectrum at the same time, maybe not exactly in the same space, but different users. So, and for example, we do have 14 gigahertz of continuous unlicensed band between 57 and 71 gigahertz. I think we should be able to tap in, or cellular providers would be happy to be able to tap in a way that works for all. Yeah? Mm-hmm. You're muted.
Anyone else? Okay, how about this question? This is a 12 gigahertz question, and the question basically is, should it be used for mobile comms, or are there different use or better use cases for it? Andrew, let's start with you.
Well, of course, this is under discussion at the FCC. We went through a comment round, and there's a lot of discussion on both sides of this. But the question comes down. The 12 gigahertz band is specifically about whether the non-geostationary fixed satellite service can share with the mobile broadband systems, and I think that's not a sure thing. And so I guess the question at this point is, do you want to have ubiquitous mobile systems, or do you want to have good quality of service and assured spectrum for non-GSO FSS? And I'm not going to take a position one side or the other on that, but I think this is more of a coexistence issue than sort of a which one is better kind of thing.
Monisha, I bet you have something to say here.
Yeah, I think I'm actually from a research point of view, I think that is the next band to really look at carefully to see how this sharing can happen. Again, it is going to be shared, as all new spectrum that comes up is going to be shared. I think the FCC raised and asked a number of questions in that proceeding, looking for answers. There are comments, it's still open for comments. They brought up the question of whether indoor sharing can be done in that band, similar to what we did in the 6 gigahertz band. So it definitely it sits nicely in between millimeter wave and sub-6. It has nice properties of both. And we definitely have to move up in the frequency. Right now it's sub-7 and 24. There is a whole swathe of spectrum in the middle that needs to be explored more, and the FCC will be looking at all of that spectrum for future applications.
Thank you much. Alex, would you like to chime in?
I can only just say that from our perspective, this is one band that we are seriously looking for 6G. And we think it is also very important to enable coverage. And for that reason, use of the techniques that are already used in 5G to basically provide coverage like massive MIMO are the techniques that we are looking for this band.
Very good. Joseph, how about you?
I think that everything that needed to be said has been said already.
Very good. Yeah, 12 gig is kind of a sweet spot between propagation and bandwidth, so I can see where that happens. Should we be changing the way that spectrum is allocated or regulated? Just got a question in that way. If we're going to see more private networks, more unlicensed private networks as well as licensed private networks, is that something we should, the FCC, we should be talking to them about doing or doing from a theoretical perspective? I'm going to start with you, Manisha.
So there has been a lot of discussion about allocating separate spectrum for private networks, and I think there are pros and cons for doing that. That's a discussion that is worth having. But on the other hand, I don't think you have to wait for that before private networks roll out. CBRS is a perfect spot for private networks to roll out in, and they are rolling out already. And in my mind, actually, that's a very exciting space to see how this whole business model around private networks takes off. And I'm sure if it is successful and it requires more spectrum, FCC would be open to looking at maybe dedicating spectrum to private networks. It hasn't done that so far, even though people have asked for that.
Andrew, I know you're into this very deeply. What do you think?
Yeah, I mean, private networks is a big use case for CBRS. I would say, though, that the FCC, I believe, took a step backward during the CBRS proceeding. Originally we were supposed to license CBRS on census tract areas, which were very localized, as small as a couple of blocks. That would have been ideal for individual private users to have acquired spectrum at a reasonable price, but they decided to go county-based instead, which made it quite a bit more expensive. So in that sense, yes, in the future, looking at private network models and things like that, I think we need to look at more smaller geographic areas, make license costs less.
Thank you, sir. Joseph?
Yeah, I would like to say that particularly if we are more comfortable doing this at higher frequencies, millimeter wave and higher, compartmentalization of the spectrum when it comes to geographical areas makes perfect sense. So we may want to start increasing the granularity of how we allocate frequencies, where we allocate frequencies. Absolutely.
Perfect. And Alex?
I think this sharing between, licensing for local licensing for private networks will actually make coexistence mechanisms that should be natively supported in 6G even more important because of all these interference issues that will arise when we have dense deployments of private networks. There should be a mechanism that technology can implement and deal with interference as opposed to having a management of channels that would have to be allocated based on the channel models that are used in that management database.
Thank you very much. So we are down to about 3 or 4 minutes. I have one question left that I'd like to get out there. Then I'll give each of you a few seconds to say whatever you want to say to close out the session. So the question is, for all the press millimeter wave spectrum is getting in 5G, the real workhorse has been mid-band spectrum. Do you see any potential for spectrum between 8 to 14 gigahertz to support relatively wide area deployments in 6G? Joseph, let me start with you.
Well, I believe that this frequency range offers a sweet spot, as was mentioned before, between available bandwidth, propagation, more than what you have under 6, not as much as what you have above 30, 60, 100, you name it. So there is an opportunity. Now, has there been, is there enough technology developed to support this? Because again, if you look at where our colleagues working on hardware are doing, it's mostly under 6. We have many people who get excited with the higher frequencies. Well, we need to align hardware technology. I think we are quite good with the software and then policy, but there is an opportunity, absolutely.
And yeah,
Andrew?
Sorry, I agree with what Joseph said, and in fact, in various places, some of the spectrum from 7 to 8 and 9 gigahertz is being looked at as possible for 6G. But I'd have to reiterate what I said earlier: is before we jump and try to relocate the systems, a lot of them government systems that are in that band, we need to take a closer look at what we're doing with the spectrum that has been being used by previous generations. And let's see if we can recycle that before we start grabbing more and kicking the federal government out.
Right. Manisha, what is your take on that?
I think just reiterating what's been said, that yes, there's spectrum there, but no, it's not empty. There is stuff in there. It's not going to be easy to find spectrum and reallocate it or make it share. But absolutely, the investigation and the research to build systems in those spectrum bands should continue.
Thank you very much. And Alex?
I just want to add that in terms of the possible technology, I think even though the frequency band would be higher than current, for example, 3.5 gigahertz deployment, in terms of what can be done to compensate for that in terms of coverage, there are techniques like massive MIMO that can be utilized to provide similar coverage. So we don't need to actually have more dense deployments, but rather reuse existing sites and improve technology so that we maintain the same coverage.
Okay, great. So we're down to about our last 2 minutes. So I would like each of you to do a brief shot on what you think the most important issues will be facing spectrum sharing going forward, not just in 5G, but in 6G as well. And Joseph, I'll start with you.
So knowing me, I just highlight the spectrum sharing issues above 100 gigahertz. I want to emphasize that we cannot just keep writing papers saying above 100 gigahertz, you have all this bandwidth, because the reality is that we don't. We have to coexist with users who were there first, with users who are far, actually on satellites, and we can interfere with them. But that's great. It means that it's time to not just do the first works at any frequency, but actually start working on hardware that is ready to support sharing solutions, software that is ready to control in real time when transmitting at terabits per second this hardware. So there are plenty of opportunities. I don't like to call them challenges. There are plenty of opportunities also above 100 gigahertz.
Thank you, Joseph. Alex, what about you?
I think if you talk about sharing between operators, the main challenge would be maintaining QoS, and I think we can achieve that if we have the right approach for the sharing. So if the technology enables it, it's possible to have maintaining QoS with spectrum sharing and get all the benefits with spectrum sharing, like unlicensed spectrum, where you get high peak rates, but you have poor QoS. So I think that's what we need to focus in terms of spectrum sharing.
Okay, Manisha?
Yeah, I'd like to, just re-emphasize something that actually Andrew brought up some time back, which is we need to build up on data-based, not database, but data-based spectrum sharing, where we look at the data, we look at what we're actually measuring to refine our propagation models, to look at how spectrum is actually being shared on the ground, and feed that data back into refining our spectrum sharing models and build better ways to share spectrum.
Thank you, Manisha. Andrew, we may not make it, but go.
Well, only two things: realistic interference criteria and improved propagation models.
Excellent. Ladies and gentlemen, I want to thank you. This has been an extremely informative and exciting session. I just want to thank you all for participating. There's some questions we didn't get to. I'll see how we can answer those going forward after this is done. In the meantime, thanks again. I hope you enjoyed it as much as I do, and you all take care. Bye-bye.
Thank you.
Thanks.